Molten salt reactors for the production of electrical power were studied at Oak Ridge National Laboratory from 1957 to 1960. Design studies and technological developments strongly indicated that molten salt breeder reactors operating on a thorium cycle could be developed to produce low-cost electricity and conserve our uranium resources. A reactor experiment, however, was required to demonstrate the feasibility of this unique high-temperature fluid fuel reactor concept. As a result, the United States Atomic Energy Commission in 1960 authorized the laboratory to design, construct, and operate the molten salt reactor experiment, also known as MSRE. Preliminary design of the reactor began in May 1960. Technology developed by the earlier aircraft nuclear propulsion program at the laboratory was used as a basis for designing the MSRE. The molten salt fuel for this reactor is radically different from that used in solid fuel reactors. Here, salt flows from a pipe which is heated to keep the salt molten. At 1200 degrees Fahrenheit, the salt does not react with air. It flows like water, but does not boil. The molten salt reactor experiment utilizes a fuel system which includes the reactor core, in which heat is generated, a heat exchanger for transferring heat from the fuel salt to coolant salt, a sump-type centrifugal pump for circulating the fuel, 3 salt storage tanks, and the connecting piping. The MSRE coolant system consists of a circulating pump, a salt-to-air radiator, a salt storage tank, and the connecting piping. Both systems were designed for 1300 degree Fahrenheit temperature and 50 psig pressure. MSRE is a circulating fuel graphite moderated single region reactor capable of generating 7,500 kilowatts of heat. During operation of the reactor, the fuel, which is nearly as fluid as water at the elevated temperature of 1170 degrees Fahrenheit and 20 psig, enters the flow distributor near the top of the vessel and spirals downward in turbulent flow through the space between the vessel and core can. The fuel is then directed upward in laminar flow through channels machined in graphite bars of the core matrix, where heat is generated by the fissioning of uranium-235. The fuel leaves the reactor 40 degrees hotter than it enters. A simple control system of 3 flexible control rods helps to regulate the power and temperature. The fuel pump, operating at 1,200 gallons a minute, obtains its suction directly from the reactor. At maximum power, the salt, which is now 1,210 degrees Fahrenheit, is discharged by the fuel pump and flows through the primary heat exchanger and then back to the reactor. Gaseous fission products, which interfere with the chain reaction, are removed from the circulating salt stream in the pump tank. The coolant salt is circulated by a sump-type centrifugal pump, similar to the fuel pump. It flows through the heat exchanger and leaves at 1,070 degrees Fahrenheit after a temperature rise of 60 degrees. Heat from the coolant salt is transferred to air in the radiator. Supplied by axial flow blowers, the cooling air is forced across the radiator and up the stack. Major components of the fuel and coolant salt circulating systems are connected by 5-inch piping and smaller fill and drain lines. During operation of the reactor, the molten salt is held in the whole system by special freeze valves. The fuel, solid at room temperature, is composed of lithium, beryllium, zirconium, and uranium fluoride salts. A third of the uranium is fissionable U-235. The coolant is a fluoride salt mixture like the fuel, but it does not contain uranium or zirconium. These mixtures were produced at the laboratory by using techniques developed during the aircraft nuclear propulsion program. The salt-containing piping and components are fabricated from Hastelloy N, a special nickel-molybdenum alloy developed at Oak Ridge, which has good resistance to corrosion attack by fluoride salts up to 1500-degree temperatures. The MSRE was designed to utilize the 1954 aircraft reactor experiment facilities. The ARE was the first molten salt reactor to use circulating fused fluorides as fuel. It operated at 2,500 kilowatts in this building. Building modifications extended from early 1961 through mid-1962. The MSRE fuel storage cell and other areas are new, but most of the former facility was modified only slightly. The fuel circuit steel containment vessel, 24 feet in diameter, had to be lengthened. It was then stress relieved by gas heating. The vessel is located in another cylindrical steel shielding tank. For biological shielding, the lower portion of the annulus between the tank and vessel was filled with magnetite sand and water, and the upper end with magnetite concrete. The cover for the containment vessel consists of 2 layers of 3.5-foot thick magnetite concrete blocks, separated by a welded stainless steel membrane. The concrete serves as a biological shield and as a support structure for the pressure-tight cell. Considerable excavation was necessary at the fuel storage cell to permit gravity drain of fuel from reactor to storage tanks. The cell's bottom and sides are stainless steel, backed by heavily reinforced concrete. This pressure-tight cell is also covered with 2 layers of reinforced concrete blocks separated by a welded stainless steel membrane seal. Dished heads for the reactor vessel were cold pressed from 1 1/8 inch thick Hastelloy N alloy plates. The reactor vessel's fuel inlet flow distribution channel was also cold formed, as were most of the Hastelloy N alloy parts. Some development work was needed to fabricate major components. It was found generally that Hastelloy N presented no more problems than other high nickel alloys or stainless steel. Assembly of the reactor vessel began in mid-1962. By the fall of 1963, special graphite, with low salt absorption and low permeability to gases, had been commercially produced and precision machined. The reactor core of nearly 600 vertical graphite bars was carefully assembled on a graphite lattice within a clean room. A removable control rod thimble assembly for the reactor was fabricated separately. The 5-foot diameter reactor with core and control rod assembly weighs about 9 tons. This special shipping fixture held the reactor vertical during its journey from shop to reactor site. The horizontal shell and tube primary heat exchanger is about 8 feet long. Its U-shaped tubes, a 1/2 inch in diameter, were fusion welded and furnace back brazed in a hydrogen atmosphere to the tube sheet. The bundle contains spacer bars tightly laced in 2 directions through spaces between the triangular pitched tubes to eliminate flutter and vibration. The fuel salt pump bowl serves as the pump sump and normal volume to allow for expansion of the salt. This fuel pump rotary element with water-cooled drive motor, bearing assembly, bolt extensions for remote replacement, and impeller circulated molten salt at 1200 degrees during the non-nuclear run-in test. The salt-to-air radiator tubes, each 3/4 of an inch in diameter, are arrayed in banks of 12 tubes each, Special assembly fixtures were required to accurately position the tube banks and subheaders for welding and assembly. The radiator enclosure and coil were fabricated separately, then assembled after removing one end of the enclosure. The enclosure, which supports the radiator coil, is a furnace containing electric heaters to prevent uncontrolled freezing of the salt. Adjustable doors and dampers control airflow through the radiator to regulate heat removal. Tanks provide safe storage of salt mixtures when the fuel and coolant salt circulating systems are not operating. These include 2 fuel storage tanks with bayonet tubes and steam dome in which fission product decay heat is removed by flashing water to steam. Several thousand high-integrity reactor-quality welds of Hastelloy N alloys were made during fabrication of major components. The history of each was recorded for future reference. Installation of fuel circuit equipment in the reactor cell began in January 1963 with the placement of the thermal shield base and cylindrical section. The thermal shield is a double-walled stainless steel vessel which surrounds the reactor and shields equipment in the cell from neutron fields. The annulus is filled with water and carbon steel balls for primary shielding. The shield also provides a support for the reactor vessel. One objective of the MSRE was to ensure remote replacement of all equipment in the reactor cell. To locate equipment during installation and replacement, a large assembly fixture was constructed outside the cell on which the reactor, fuel salt circulating pump, primary heat exchanger, and connecting piping and disconnects were accurately located by optical tooling methods. After the connecting piping and auxiliary equipment were attached by using the fixture, the reactor was lowered into the thermal shield. Connecting pipe bends and welds were normalized at a temperature 450 degrees higher than normal salt operating temperature to minimize movement of pipe disconnects after the fuel salt had circulated. The same procedure was followed for the fuel salt circulating pump bowl and furnace. Installation of the pump was completed with the addition of the pump rotary element, drive motor, auxiliary piping, and electrical connections. Special freeze flanges in the fuel salt circulating piping permit the removal and replacement of major components, such as the heat exchanger. All components and connecting piping in the salt circulating systems are heated electrically to maintain the system above the salt freezing point of 840 degrees. The equipment is preheated before salt is added. The fuel storage tanks and related equipment were installed by using assembly fixtures, and the same procedure was utilized for the main fuel circuit. The fuel storage tanks with steam cooling systems were positioned inside the electric furnaces. The salt piping and all auxiliary services, including instrumentation and controls, were thoroughly checked for leaks and electrical continuity. Since heaters and thermocouples as well as the coil were installed in the radiator enclosure at the shop, no additional work was required before the radiator was placed in the coolant cell. Installation of the radiator, salt storage tank, and circulating pump completed the coolant circuit. The MSRE incorporates some novel features and components designed and developed specifically for molten salt reactors. Performance data on these items permit the evaluation of ideas and principles which might be employed in breeder-type molten salt reactors. It is planned to remove impurities and recover uranium from the fuel salt in this on-site processing facility. The sampler enricher is a unique device for sampling and adding fuel during full power operation of the reactor. A power-driven cable remotely lowers a small bucket into the liquid salt of the pump bowl, and then raises the bucket into a manipulator area for transfer to a shielded container. More than 300 samples have been obtained routinely by this method. When needed, fuel is enriched by lowering a bucket of enriched U-235 and dissolving it into the circulating fuel salt stream. This eliminates the need for excess fuel reactivity. The fuel has been enriched 3 times by adding 114 buckets of enriching salt. Another feature of the MSRE is its high-speed digital computer. The computer does not exercise direct control over the reactor, but collects and displays data and performs online calculations for immediate and long-range purposes. With the final addition of 680 grams of enriched uranium into the fuel stream by the sampler enricher, the molten salt reactor experiment went critical on June 1st, 1965. Low-power nuclear experiments lasted about a month. After final preparations, power operations began early in 1966. During the year ending in January 1968, the reactor was critical over 75% of the time, producing nearly 41,000 megawatt hours of heat. By this time, many of the test objectives had been reached. It has been demonstrated that MSRE can be operated safely and reliably, and that maintenance of radioactive equipment has been accomplished with minimum difficulty. Nuclear characteristics were extremely close to predicted values, and the system was dynamically stable at all power levels. Graphite and Hastelloy N specimens similar to these have been removed from the fissioning fuel stream in the reactor core. Examination of specimens in hot cells indicated no deleterious corrosion or structural change after salt had been circulated in the fuel system for more than 6,000 hours. In that time, the fuel proved to be stable to radiation and heat. The reactor, with its 1200-degree core outlet temperature, is one of the highest temperature reactors operating today. As a result of this success, ORNL is proposing to develop a thermal breeder reactor. This is one which produces more fissionable material than it consumes. Thermal breeders have many practical construction and operating advantages, and the molten salt reactor appears to be a very attractive thermal breeder. Molten salt thermal breeders should have a low inventory of fissional material, which means that the amount of uranium needed to fuel the reactor is low. In the design of a 2-fluid molten salt breeder, the fuel salt mixture of lithium, beryllium, uranium fluorides is pumped through graphite tubes in the reactor core, where heat is generated by fissioning of uranium, and then through the primary heat exchanger, where the heat is extracted. The fertile or blanket salt surrounds the core where additional heat is generated. It is then pumped through the blanket heat exchanger, where this heat is extracted. The blanket salt mixture contains thorium, which is converted to fissionable uranium atoms more rapidly than they are consumed in the reactor fuel. The heat produced in the fuel and blanket streams is transferred by an intermediate salt heat transfer system to a supercritical steam-generating electrical system. In an alternative design, one salt containing thorium and uranium circulates through the reactor vessel and heat exchangers. This simpler single-fluid reactor is also a promising breeder if problems of on-stream fuel processing can be solved. ORNL studies indicate that molten salt breeder reactors should be able to produce electricity at low cost and with the high efficiencies of modern steam plants. Thus, the laboratory's important goals of nuclear reactor development converge in the molten salt breeder reactor. The search for a stable fuel at high temperature, the urge for fluid fuels, and the capability of providing an infinite supply of electrical power at low cost.